Hi everyone, how's it going? We're going to move on to the next section now, which is 7.2, called trigonometric integrals. And so as the name suggests, we're going to be taking the integral of things that involve a lot of trigonometric functions, so sine, cosine, tangent, and so on. And here is where a lot of these identities, like the half angle formula or the Pythagorean identity or the reduction formula or like the power to sum or the sum to product to sum formula, things like that, they're going to come in handy here. So they may have seemed very random back when you learned them in trig, but we're going to use them very extensively to do these integrals. So we'll start off with just an example to kind of show us what's going on. So say we want to know the integral of cosine cubed x. Okay, at the moment we can think we only know the integral of just cosine. Now can we do like any of the techniques that we have? Can we do u substitution? Can we do integration by parts? And the answer very quickly becomes, for one of them, u substitution won't do anything for us. You know, what's the only choice for u is cosine. Well, that's not going to do much. If you let u be cosine, then du will be negative sine x. So then du over negative sine will be dx. So you'll get the integral of u cubed du over negative sine x. And this makes things even worse. It doesn't do anything for us. And then integration by parts will again make us run into trouble. So these two techniques that we've talked about won't help us here, so we're going to have to resort to using some trig identities, or at least simplifying this, changing its form a little bit. So step one is we're going to use the fact that sine squared x plus cosine squared x equals 1. And then when we subtract sine squared, we see cosine squared is 1 minus sine squared x. So we're going to use this. How are we going to use it? We're going to rewrite the integral as cosine squared times cosine, right? If you have x squared times x, that's x cubed, where x in our case is cosine. So we broke it up into this, and now this cosine piece will replace with that. So cosine squared here is going to get replaced with that. So now we have 1 minus sine squared x times cosine x. And now let's distribute the cosine. So this becomes the integral of cosine x minus cosine x times sine squared x. And now we can split the integral up into two pieces. So the first piece is cosine, and the second piece is this. Okay. Now this integral we know how to do. That integral is just sine. So this just gives us sine x. And then we're still left with this guy. But now we can use u substitution on this integral. If we let u be sine x, then du will be cosine x dx. And so subsequently du over cosine x will be equal to dx, and that's perfect. So we get sine x minus the integral cosine x times u squared times du over cosine x. And now this is perfect because the cosines cancel out. And so we just have the integral of u squared, which is 1/3 u cubed. So this is sine x minus 1/3 u cubed. But what is u? It was sine. So this will be sine cubed x and then plus c. So that's the value of our integral. The original integral we started with is this. And so you can see that the key here was to first use some trigonometric identity that we've known, namely the Pythagorean identity. Sine squared plus cosine squared equals 1. And we'll use the other ones as well here in a second. Okay, so now let's jump to this one. So now let's do the integral of sine to the 5th x times cosine squared x. Okay. Now again, we're going to want to exploit some of the trigonometric identities. But first, we're going to write the sine to the 5th as sine squared times sine squared. Or I'll put sine first. Sine x times sine squared times sine squared times the cosine squared. Okay. Now, it may seem weird why we're doing this, but notice this is just the same as x times x squared times x squared. That's x to the 5th. So I just broke this up. And the reason why I broke it up into two different sine squareds is to use the Pythagorean identity. Namely, or a variation of it, the one that we saw, is that sine squared is the same as 1 minus cosine squared. Pythagorean identity is this. That's the Pythagorean identity. We are just using a variation of it because we just subtracted cosine squared from both sides. That's equal to sine squared. So sine squared x is 1 minus cosine squared x. So yeah, this was a Pythagorean identity. Okay, very cool. So as a consequence of this, we get, the following. And then again, the cosine x just comes along for the ride. Oh, sorry, cosine squared. That one. Now this looks, it looks like we took a hard problem and made it even worse. But actually, at this stage, we can make a substitution. If we let u be cosine x, this would mean that du is negative sine x dx. And this would mean that du over negative sine x equals dx. Okay, and that's very nice because now we get the integral of sine x times 1 minus, well, cosine is u, so cosine squared is u squared. And again, the same thing, and then another u squared. And then du over negative sine x. And what's super awesome is, look, this cancels out. Very convenient, right? It took some, whoever came up with this at first probably sat there and thought about this for a good amount of time, but we have the luxury of very good hindsight. Okay, and so now our integral, really, let's not forget about this minus sign, we'll float it out in front, is minus 1 minus u squared, 1 minus u squared times u squared du. And this is great because this is just, we need some algebra to finish this up. So if you FOIL this out, you'll get 1 minus 2u squared plus u to the 4th, and that's still times u squared, right? Because 1 minus u squared times that, 1 times 1 is 1. 1 times negative u squared is minus u squared. You pick up the same thing here, and then these two multiply to give u to the 4th, which is, after combining like terms, what we saw. Okay, so very good. So this product gave us this entire quantity. So u squared has to distribute to that entire quantity. So then now, and then du. Now we have negative integral of u squared minus 2u to the 4th plus u to the 6th. And now let's put this minus sign in to flip the sign on everything. So the negative hits this to make it negative. It'll hit that to be positive, and it'll hit this to be negative. Sweet deal. And now this is, this is every calculus student's dream integral. Not too much work to do here. You just apply the power rule a bunch of times. Everybody loves to do that. So this is now negative 1/3 u cubed plus 2/5 u to the 5th minus 1/7 u to the 7th plus c, and then once we substitute back u as cosine, we get the final answer. And that is that's a crazy, crazy answer, This looks very elaborate. But this elaborate answer is the integral of what we started with. It's pretty crazy. Okay, so the next integral that we're going to deal with, or other integrals, may require these following identities. You may or may not remember them. They're the double angle identities. Double angle, yes. They're kind of a variation of the double angle. So you'll see what I'm talking about. So we'll have sine squared x is equal to 1/2 times 1 minus cosine of 2x. And then cosine squared x is 1/2 times 1 plus cosine of 2x. Okay, and then so this is 2x here, so not squared. Be very careful about that. So these are just variations on the double angle identities for cosine 2x. Remember, there's 3 of them. So there's just variations on those, on 2 of those. And another way of writing these, of course, is 1/2. If you distribute the 1/2 minus, and then also here. Okay, so we'll want to use these sometimes. Okay, so let's say we want to find this integral now. The integral from 0 to pi of sine squared x. This integral looks, pretty tame, but with our known methods, we still don't know how to do it. But if we use this identity, it's perfect now. So we're going to use this identity to rewrite sine squared like this. So it'll be 1/2 minus 1/2 cosine of 2x. So we literally just made that substitution. We just replaced sine squared with this. And then you could break this integral up into two pieces. So the first integral is just 1/2 x evaluated from 0 to pi, which, you know, the 0 is not going to do anything, so when the dust clears, this will just be 1/2 times pi, which is just pi over 2. So effectively, this integral became 1/2 x evaluated from 0 to pi. That's 1/2 times pi minus 1/2 times 0, which is just pi over 2. So we just get that. And then to handle this integral, we'll do some u substitution. We'll let u be equal to 2x. So du is 2 dx. So all we pay, the price is just division by 2. So du over 2 is dx. So the only price we pay from going from dx to du is we have to divide by 2. And then what are our new limits of integration? U of 0 is still 0, but u of pi is 2 pi. So then our integral transforms into minus 1/2 integral from 0 to 2 pi cosine of u du over 2, but this du over 2 is the same thing as multiplying by 1/2. So up front we'll have a 1/2 times this new 1/2 coming from here, will make this a fourth. So this will be a fourth, and this just goes away. Okay, and then this becomes pi over 2 minus 1/4, and then remember the integral of cosine is sine, and then we evaluate that from 0 to 2 pi. So this is pi over 2 minus 1/4 times sine of 2 pi minus the sine of 0. But what's interesting enough is both of these quantities are 0. They're angles that end at the same place. They're coterminal. One starts here, the other is just 360, but you end up back at the same spot, and the sign here is 0. So this doesn't contribute anything, and our final answer becomes pi over 2. So the integral from 0 to pi of sine squared is that. Pretty neat. Okay. Let's just keep moving on with the examples. A lot of this is just practice. Learning how to be proficient with these integrals and their techniques is all practice, so we're just going to keep practicing. So next up, we have sine to the 4th x dx. Now again, this doesn't have like a cosine companion. You know, the earlier examples, there was cosine floating around too, so we could leverage that and try and do u substitution with that. But here we don't have that, so we're kind of stuck. But again, we know the fact that sine squared is 1/2 minus 1/2 cosine of 2x. We do know that. And so we're going to rewrite this as sine squared x times sine squared x. The 4th power splits into 2 second powers. And then we're going to get a copy of this for each sine squared. So this is, and maybe, yeah, maybe the better way to rewrite this in this example is the 1/2 minus this. So the first copy gives us a 1/2 times this, and then the second copy gives us the same thing. Okay, now these two 1/2s, remember, this is like 1/2 times this times 1/2 times that. So we have 4 things being multiplied. The order that we multiply these doesn't matter. So I can do the 1/2 times 1/2 first to get a 4th and pull that out in front. And then what I'm left with is this. And now I'm going to FOIL this out. So when you FOIL this out, you get, 1 times 1 and so on. So 1 minus cosine of 2x minus another cosine of 2x, and then plus cosine squared of 2x. Maybe I'll put a parentheses here for clarity. So here this means cosine of 2x times cosine of 2x. That's what the cosine squared here means. And yeah, this notation can be very tricky because a lot of people assume that cosine squared x is the same as cosine of 2x. But this is not. This says, give me an angle x, I'll double it and then take the cosine of it. This says, give me an angle x, I will find the cosine of that angle, that length, and then square that answer. So these are not the same. Like, for example, cosine, let's say f, we call the first one f of theta is cosine 2x. Oh, I'm so sorry, f of x. And let's call g of x cosine squared x. Then f of pi over 6 would be the cosine of 2 times pi over 6, which is the cosine of pi over 3, which is 1/2. But g of pi over 6 would be the cosine of pi over 6. You take that number and you square it. So cosine of pi over 6 is root 3 over 2, and you would square that to get 3/4. So notice they're not the same. And so cosine squared of 2x is kind of doing both. First you would double the angle, then compute its cosine, get that number, and then square that final number to get the result. Okay, so hopefully this makes sense. Okay, and so then these are like terms, and we'll already split the integral up into each piece, so we'll split up into 1/4. The 1/4 hits every single term. So there's 1/4 here, just 1 dx, minus this one and that one combined to give a -2 cosine of 2x. Oh, sorry, the minus sign I already took into account. And then when this 2 floats out, 2 times the 1/4 will actually just give us a 1/2. So there's that. And then this one, still just hanging out. Okay, we know this one, this is just x. So this integral gives us 1/4 x minus 1/2. And we saw what the integral of this is. You end up just doing a simple u substitution, but that u substitution ends up just dividing by a 1/2. So this would be 1/2 times 1/2 sine of 2x. Notice that the 1/2 sine of 2x, if you take its derivative, it's going to be equal to 1/2 cosine of 2x times 2 by the chain rule. And notice these will cancel to give you cosine 2x. So that is what we want. That is the correct integral. So yes, now the 1/2 and the 1/2 do give us a 1/4. So we have minus 1/4 sine of 2x. And now we're kind of stuck with this guy. Okay, this one we're stuck with. We kind of don't know where to go with this. But now we're going to use the other version of that formula, which related to cosine. So the formula said cosine squared x is 1/2 times 1 plus cosine of 2 times x. So whatever this thing x is, remember x is just a placeholder. It could be like 13,000 x squared plus 14x minus the square root of pi. It could be as complicated as you want. It's just saying that whatever x is, in this cosine expression, you end up doubling that. And so if x is 2x, we know that cosine squared of 2x, so if x becomes 2x, this is now 1 plus cosine of 2 times whatever x is, which is 2x. So 2 times 2x. Which tells me that cosine squared of 2x is actually 1/2 1 plus cosine of 4x. And so we're going to use this over here. So now this becomes 1/4 x minus 1/4 sine of 2x plus 1/4 times the integral of 1/2 times 1 plus cosine of 4x. This is very, I told you things would get lengthier and lengthier. So we're just going to keep redefining what is lengthy and what is not lengthy. And so again, this 1/2 will float in front of the 1 out, and so 1/4 times 1/2 will give us an 1/8. And then it'll be integral and then again, we can split this integral into 2 pieces. So 1/8 integral of just 1 plus 1/8 integral cosine of 4x. Okay, this one we know how to do. Not bad, it's just x. So we get 1/4 x minus 1/4 sine 2x plus 1/8 x plus 1/8 times, and then how are we going to deal with this integral? Well, we're just going to use u substitution. So if u is 4x, then du is just 4 dx, and du over 4 is dx. So this becomes 1/8 integral cosine of u du over 4. And you're going to see this trick happen a lot. If you just have cosine of some constant times x, its integral is just going to pick up 1 over that constant, and then it'll turn it into just the integral of, cosine, whatever it is, which will turn into sine. So you can maybe start to come up with a formula. By formula, I mean this. The integral of the cosine of kx is just 1 over k sine of kx plus c. And similarly, the integral of sine kx will be negative 1 over k cosine of kx. We might prove these in class, but those are pretty handy formulas here. So we've seen examples of this where k is 2 and like k is 4. Okay, so then again, finally, this 1/8 times a 4th gives us a 1/32. So we have 1/4 x, and this 1/4 x and this 1/8 x are like terms. So we can just think about it as just adding 1/4 to an 8 for a second. So 1/4 is the same as 2/8. So when they add, they give 3/8. So we get a 3/8 x out of that. These combine to give 3/8 x minus 1/4 sine 2x. And then this 1/4 times this 1/8 is a 1/32. And the integral of cosine is sine. And then our u was 4x. And so now we're done. I'm just making sure this is right. Yes. So then this is the final answer. Very, very pretty involved, right? A lot of steps. Okay, very cool. So yeah, the book presents this strategy for doing these. I won't talk about it in particular because I think it's good to just reason these out, but in class with the table, because I can pull it up with the screen, we can go over it. But for now, let's jump to the other type of very common trigonometric integral is, the reason why sine and cosine being next to each other was nice is because the derivative of sine is cosine. And there was a relationship between sine squared and cosine squared and things like that. Now, if you take that Pythagorean identity, sine squared x plus cosine squared x is 1, and you divide both sides by cosine squared, meaning you divide each term by cosine squared, you get a variation of that. So sine squared over cosine squared is tangent squared. And then cosine over squared over cosine squared is just 1. And then 1 over cosine squared is just secant squared. You get a variation of the Pythagorean identity, which for all intents and purposes is just called the Pythagorean identity as well. Now this is already one relationship between tangent and secant, but that's good. But there's also derivative formulas that connect them as well. Remember, the derivative of tangent was secant squared, and the derivative of secant was secant x times tangent x. So it's not too surprising that we will be able to use kind of these properties here to deal with integrals that have products of different powers of secant and tangent. So for example, let's look at this. let's say we want to find this integral. Yes, that's right. Now we have to be careful because in the other one, when we made our decision on what to do, we had to be mindful of eventually we did a u substitution. When we do a u substitution, one of these guys is going to come up, a secant squared or a secant tangent, depending on which of these we let be u. So if u is tangent, we get that. If u is secant, we get that. So what we're going to do is, how about we do this? We write this as tangent to the 6x times secant squared times secant squared. And now we have tangent to the 6. One of these secant squareds we'll replace with this because that's what it's equal to. But the other secant squared we'll just leave. And this will become parent y in a second. So what we're going to do is we're going to let u be tangent x. And because of our friend here, this means that du is going to be secant squared dx. And this means that du over secant squared x is dx. And that's why we left a secant squared. Normally with sine and cosine, we would just leave one power of sine and one power of cosine, because the derivative would then cancel out. But here we need to keep a secant squared to cancel out. So then we have the integral of u to the 6th times u squared plus 1 times secant squared x du over secant squared, which is perfect because these cancel out. And so now we have the integral of u to the 6 times u squared is u to the 8th, and then u to the 6 times 1 is this. So we're left with 1/9 u to the 9th plus 1/3 u to the 3rd plus c, and then substituting back for giving us tangent in these spots. And there we go. Sorry, I don't know why. I said u to the 6 times 1 is u squared. It's not. I think I might have read this power wrong. U to the 6 times 1 is u to the 6th. So I'm so sorry. This is 1/7 u to the 7th. So we get this. This is the final answer. Okay, very cool. So hopefully this makes sense. The strategy is slightly different because of this. So we'll either need to leave off a secant squared, or we'll need to leave off a secant times tangent to cancel out. Normally we would just leave a sine or a cosine, but because the derivative of these guys, which will be u, in one of the cases either one can be u, we need these factors to stay out to cancel. Okay, so now let's look at this one. So we have tangent to the 5th theta times secant to the 7th theta. Okay. Now the nice thing about what we did previously is the power of secant was even, meaning that we were able to write it as, it was secant to the fourth as secant squared times secant squared. The problem here is we won't be able to do that. We can break this up into secant squared times secant squared times secant squared, but then that leaves us with a secant x, which is bad because then if we let u be tangent, we need a secant squared to be left to cancel out. And so this is not going to work. It's not going to work out so well. Because these secant squareds will be converted to these tangent squared plus 1, so they'll be off limits. So the guess is we probably need to evoke this strategy and actually turn this into a form where the tangents actually give us something. So if you rewrite this slightly, you could see that tangent squared is secant squared minus 1. And this is nice. We have an odd power of tangent. So we're going to rewrite this as tangent squared times tangent squared times tangent. And then times secant theta times secant to the 6th theta. Now why do we do that? So we broke these two up into tangent squareds to be able to use this. And then the remaining tangent, we wanted to pair with one of the secants so we can use this here. This is the key there. And then we were just, as a consequence of that, we're left with 6 more powers of secant. So now we'll have the integral of secant squared theta minus 1 times secant squared theta minus 1. And then I'll write the secant to the 6th here. And then our nice factor secant theta tangent theta I'll write at the very end. And now you guessed it, we're going to let u be what? Secant. So if u is secant, that means that du is the derivative of secant, which is secant theta tangent theta d theta. Oh, that's awesome. See, that's going to cancel out with that. So then du over secant theta tangent theta is d theta. So now our new integral becomes u squared minus 1, u squared minus 1, u to the 6th, and that's awesome. This extra factor cancels out perfectly. And so we just have u's. Look at that, that's beautiful. So then now we have, I'll put this u to the 6 out in front. Okay, and then again, after some algebra, this turns into everybody's favorite type of integral. You just use the power rule a bunch of times. So this becomes, once you FOIL this out, u to the 4th minus 2u squared plus 1. And then distributing the u to the 6th, u to the 10th minus 2u to the 8th plus u to the 6th. And then power rule gives 1 over 11 u to the 11 minus 2 over 9 u to the 9 plus 1/7 u to the 7th plus c. And then finally, letting u be secant, we get our answer secant to the 11th very elaborate answer, right? Very crazy. So it's pretty cool how all of this stuff just comes together and works out so nicely. And yes, as promised at the beginning of this class, I told you would realize very soon that it's much harder to take integrals in general than derivatives. Derivatives, you just use the rules and nice, we're done. With integrals, there's a lot more thinking involved. Okay. And then these next set of integral formulas, they're just something we'll want to keep in our back pocket because they come in handy sometimes. We proved one of them earlier, the other one we won't prove. We're just going to use them. So one is the integral of just tangent is the ln of the absolute value of secant. And then the integral of secant becomes the ln of secant x plus tangent x plus c. So these are just little tools that we're going to use, just like with the formulas that we've been using or the Pythagorean identities. They're just something we want to keep in our back pocket. Okay, and so let's see how they're used. So let's say we want to find the integral of tangent cubed. So again, now the secant partner is gone. You know, this was just like when we did sine to the 4th or something like that. It's not so easy. We don't quite have, you know, the secant that we need. Now we can introduce it, if we'd like to, using the Pythagorean identity that relates secant squared to tangent squared. But we want to do that and make sure, you know, that it'll be able to work out, that after u substitution, everything will cancel. So what we're going to do is we'll write this as the integral of tangent squared times tangent. And then remember, 1 plus tangent squared was secant squared, meaning that secant squared minus 1 is tangent squared. We're going to make that replacement here. So this is the integral of secant squared minus 1 times tangent and then we'll distribute the tangent. So this will become tangent x secant squared x minus tangent x. And then we'll split this into two different integrals. And now you can see where this is going to come into play. Sweet. Okay, and then now we'll go back to the, or not the top, because I want to keep this. So the integral of tangent, we're going to use this. So this one will turn into the ln of the absolute value of secant x. So we still have the integral tan x secant squared x. But then this one will just be minus ln absolute value secant x. So that one we knew because of our formula. And now this one, let's rewrite this as tan x, tan x, secant x, secant x. Now why did I do that? This guy here is a perfect thing to cancel if I let u be secant. So now, if I let u be secant, then du secant x tangent x, meaning the following. Very nice. And so we get the integral of tan x secant x. This is u, and then this is du over, sweet, cancels. Man, this is working out so nice, it's crazy. And then we're just left with the integral of u, which is 1/2 u squared, but u is secant, so this is 1/2 secant squared minus ln absolute value secant x plus c. Okay, and then the last kind of set of formulas that we're going to need are what are called like the product to sum formulas. So these were the following, and you know, very few people just have these remembered, so it's okay if you look. You just need to know of their existence. And then this guy is my black. I need some new markers. These guys are basically dead, so I'll do it in green. That's one. And then, so this one is if you mixed a sine and a cosine, and then the other two are where you have sine, sine, and cosine, cosine. A and B just represent different angles. Just make sure these are right. Okay, awesome. So yeah, we're going to use these now to help us find integrals in this form. So let's say we want to find the integral of sine 4x times cosine of 5x. Okay. Now this is like in this form. So A is like 4x and B is like 5x. So using the formula, this is the same as 1/2 times the sine of 4x minus 5x, so A minus B, plus the sine of 4x plus 5x. Okay, does that make sense? Fair enough. And then the 1/2 will just float out in front as usual. And then this becomes sine of negative x plus sine of 9x Now because sine is odd, this minus sign will just pop out in front. So we get 1/2 integral of negative sine x plus sine of 9x, which again we could split this up into two different integrals. So 1/2 integral of negative sine x plus 1/2 integral of sine of 9x. And then this minus sign here can pop out in front. Okay. And so this one we know, the integral of sine is negative cosine. So when that negative hits that positive negative 1/2, you'll just get 1/2 cosine x. And then as we talked about, the integral of sine of kx is negative 1 over k cosine of kx. And in this case, k is like 9. So this is minus 1/2 times 1/9 cosine of 9x plus c. And then, 1/2 times 1/9 is 1/18, negative 1/18. And so this is the final answer. Okay, so hopefully this makes sense. Again, a lot of practice is needed to do these problems, but we'll definitely practice in our meetings in class, and you guys, feel free to ask me more questions, but that's it for this lecture. Thank you.